Welcome, fellow humans. Today's journey starts from the highlands of Solidity, crosses the hills of the Yule Intermediate language, goes through the marshes of MacroAssembly, glides over the quicksands of Pure Assembly, and finishes with a fresh breeze of Taylor. I expect you to follow along, and I assume you have set up your workspace as shown in the Advanced Blockchain Tools Setup video. Solidity. It is the JavaScript of Ethereum. It is easy to learn, but the path to mainnet can be treacherous if you venture off the beaten path and don't apply the suggested safe coding patterns. But today we are not concerned with safety. Today is an adventure. And our adventure starts with a simple algorithm. With a for loop. Our life is a finite cycle of an unknown value, so we need an unknown variable to bound this loop. We don't usually remember, but we always start from zero, conception day, and we are but a drop in a pond, but this drop must have a lipid membrane, the shell of a function. This at least double-layer lipid membrane needs to communicate with the exterior so it can be alive and useful and part of a bigger purpose than itself, so it develops pores, or channels. These channels work only with certain types of ions. In our case, our function is selectively permeable for unsigned integers of 256 bits. And this is a two-way street. The function takes in an unsigned number and lets out an unsigned number. So we now have the shell, the communication channels, and the loop of life. And we will leave the upper bound of our life cycle for Destiny to decide. And Destiny is the nickname of our unsigned integer input channel. Now, did we forget anything? Well, we forgot our purpose for existence. I mean, we can always just do nothing and wait for another input and magically not return anything like a human black hole, but even black holes bleed light and matter to the outside eventually, and we don't want to implode. Now we can always return random garbage with no correlation or causation to the input, and I bet there will be some systems wanting to interact with us just for the laughs and chaos. But well, we secretly want a purpose, even if small. It brings correlation and causation into our lives, makes things bearable, and future generations will travel through space at the speed of light because we made a function. So, there. This is it. This is also what a 5-year-old child nowadays would come up with without knowing the nth partial sum formula for natural numbers. But now, in the land of programming, we can compile this function with the MacroAssembly plugin, and we can deploy it and use it. Let's give the input 4. And we get the result 6. Which I don't like, so I'll put an equal sign here, recompile, redeploy, and test it again. And now we get the result 10. It is 1 plus 2 plus 3 plus 4. Good. Now we can take the same function concept, dress it in another language, and rebirth it with another life in another system. In our case, let's do the same thing in Yule. Yule is an intermediate language created by the Solidity team that you can use in a standalone way, but you can also use it in Solidity as inline assembly. Its main purpose is to become a bridge between EVM1 and EWASM, much like definition religion. It stood alone and it also formed the basis of many other religions and cultures throughout time. But I digress, so let's make it swift. This is the constructor code. What it does, it just copies the runtime code and then returns it. And now for our runtime code, the for loop. We are hovering over primordial waters, so there is no function concept here, but we have the building blocks to give life to its spirit. A function is a unit of computation that has a purpose, and the system's glue code directs the input to it with a switch case statement. In our case, we will compare the first 4 bytes of our call data. We first load the first 32 bytes and then shift to the right with 224 bits. And then make sure that it is 11223344. Now, I once dreamt of a digestive system-like system where the streams of data are directed to the appropriate functions by sifting the data according to the input types. But we are not in that dream, and our functions are artificially designed by our pretty uncreative minds, so our switch will just test that the outside data begins with 11223344. Otherwise, it is beyond our pay grade and the system fails. Now, Yule only works with unsigned integers of 256 bits, so we are good here. We can just read the input as the first 32 bytes after the 4 bytes from the signature. This will be our result, and this is our function's purpose. And this returns the result, which is written at position 0 in memory, and then we return 32 bytes from position 0. And now we can go to the MacroAssembly plugin, compile it, deploy, and send the same input value 4, preceded by our function signature. Ah, and we get the result 10. Good. Our MacroAssembly framework comes with some predefined macros that we can load and extend directly in the editor. So what does MacroAssembly and pure assembly have that Yule does not have? Access to the control flow. You can teleport dynamically wherever in the code you want. Well, not quite, because you need to mark all the possible jump destinations at compile time. But we don't care about teleportation now. So, the MacroAssembly framework already comes with two flavors of loops. The M4 mem, which is a for loop macro with the state kept in memory, and M4 stack, which is a for loop macro that keeps its state on the stack. Now, I created the for loop with state in memory when building the Taylor interpreter because I needed all the stack space I could get to run recursive functions, and Yule only gave me 1024 stack slots, so Taylor comes with the flavor of running either on stack or on memory frames. But now we are going to use the M4 stack macro. We will use the deployer macro, which takes care of our constructor. And then we have the M4 stack macro. This expects to find three variables on the stack: an end tag, telling the M4 stack macro where to jump after it ends, the end value for the loop, and the start value, which is 0. So let's not forget about the entrance in our function. So we load the first 32 bytes of our call data and then shift it 224 bits, which is E0. And we get the function signature, the first 4 bytes. So we have the signature on the stack. Now, if this signature is equal to 0x11223344, then we will jump to the this is the function you are looking for, which will start somewhere around here. If not, we will simply revert. So next, we load the first 32 bytes after the 4 bytes from the signature. And this is our end of loop life. So let's see what we have on the stack here. Okay, when we enter the loop, we have A on the stack, we have tag, we have end of loop value, which is also A, and the current step. What we don't have is the accumulator. So we will add the accumulator here. So it changes a bit. It changes this. So what we need to do now is duplicate the accumulator. And we need a dup4. Add the current step. Swap the old value for the new one. And pop the old value. That's it. So when the for loop ends, we just need to clear our stack. And we only remain with the accumulator value. And we return this value. So we store it at position 0 and then return whatever we find at position 0 and only take the first 32 bytes. So let's compile this, and we get the raw assembly code and bytecode. Deploy it and use the same input as earlier, value 4 preceded by the function signature. So we got an error. So let's take this transaction hash activate a debugger, and let's see what is wrong. So we are pushing a 0, we are doing the call data load and seeing the value loaded here. We are doing the shift and then equal, and it's not equal. I have another 3 here. So let's try this again. And now we have a 6. Voila. And we get 10. Great. And now we can take a look at the assembly that was produced by MacroAssembly. We are going to copy this in another file. And of course, we can also compile and deploy and interact with pure assembly directly from the plugin. Let's look at this code a bit. So, this is the constructor code, which returns the sub-zero runtime code that needs to be stored on-chain. And we can see the expanded macro content for the for statement. Let's see where it begins. It sees if the start value is lower than the end value, and if it is, it jumps into the loop and continues here with our content, our function's purpose. Otherwise, it pops the loop state from the stack and then jumps to the loop end tag, which is still on the stack. Inside the loop, and after our content, we have the loop end. This is where the step is increased. And then after the loop, it jumps back to the beginning. And lastly, we have our return code. And now we can also take the bytecode and place it in a file with the extension .hex. Compile it. Well, we don't really compile it because the result is the same, but we can deploy it and interact with it. And the result is 10. Now, after all this low-level code, let's cleanse our palette with Tailor. So we want a function with input A, and this function will be recursive, and we will keep our accumulator value with us. So I will make an internal function recursive sum that takes in the end of recursion value and the accumulator. You can think of this like the end of life and the accumulator of memories and side effects that one produces in life. Now, the accumulator grows in size while the remaining life shrinks. And if the end is lower than 1, then the side effects are all that remain. Otherwise, we call the recursive sum function and we subtract a 1 from the end of life and we add the current life value to the accumulator. And inside the body of the computation, we call this recursive sum function with a and 0. And we will call this entire function with the input 4. And I made a mistake here. This should not be an argument. It should be in the let body. So, this is Taylor version 1. Taylor version 1 has been deployed on Kovan, Ropsten, Ringby, and Gourley. And I will use the Kovan interpreter contract to execute this script. The script is compiled into bytecode, and the Taylor interpreter on Kovan is at this address. And we already have the bytecode set as call data, which we just need to run. And the return is 10. If we change the input here to 5 and recompile and rerun the call data, we get 15. Fellow humans, this is it for today, and don't forget, pleasure is the mind killer.